Greetings, Earth and Space Explorers. Welcome to Doc Waller's Earth and Space Report for August 15, 2020. I'm Dr. Bill Waller, an astronomer, science educator, and communicator coming to you today from Rockport, Massachusetts. These Earth and Space Reports are intended to engage and inform people like you who are curious about Earth as a planet, who care about our human relations with Earth's life-giving environment, and who wonder about the greater cosmos, our place in space and moment in time. Today, I will be talking about an Earth science topic that has intrigued me for several years. In Earth and Space Report number 2, I compared the warming that is produced by greenhouse gases in the atmospheres of Earth, Mars, and Venus. Today, I will focus on Earth, specifically on the waste heat that we humans produce and the consequent warming added to that produced by our greenhouse gas emissions. So I will get started now by sharing my screen and going to waste heat and share. And now make the slideshow. From the beginning. Okay, we're started. Yay. So the title of the talk is Waste Heat and Warming Climates, a New Paradigm for Energy Policy. And what is shown here is a NASA animation of the warming that has occurred on Earth over the past 100 years or so. And you can see that it starts off in the late 1800s and then moves on to the 2000s. And it seems to be getting toasty. So most of this is due to the greenhouse gases that humans have been adding to our atmosphere. These gases are carbon dioxide, methane, and other gases, along with the water vapor, but we haven't added that much more water vapor. But the CO2 in particular has been making the temperatures of the atmosphere and the Earth's surface and oceans surfaces significantly hotter. Here are the data, which I showed in Earth and Space Report number 2, and it shows that basically there has been an increase in temperature over the last 50 years of about 0.6 degrees Celsius. That has since increased into 2020 to a full 1 degree Celsius increase since the pre-industrial times back in 1880. So we definitely have clear evidence for global warming on Earth's surface. And most of this can be ascribed to the additional amounts of carbon dioxide, methane, and nitrous oxide, nitrogen oxide that we have added to the atmosphere. The carbon dioxide in particular has a very long residence time, and it's thought to be the major contributor to the excess warming. The atmosphere already has greenhouse gases. It's what's kept the Earth from freezing over for most of its 4.6 billion year old history. And so now we're adding to the mix and making life a little more difficult for ourselves. Okay, but in addition to that, there are other effects that we humans produce, and one of them is by making cities. And the cities are full of asphalt and concrete and brick, and those materials absorb more heat than the grasses and the trees. They also don't transpire or evaporate as much water, and so that leads to a urban heat island effect compared to what's going on in places where there's still plenty of greenery. So and this leads to situations which you probably are familiar with, especially if you live in the cities, that downtown can be significantly warmer than the rural and suburban regions nearby. And that's because there's been a lot of solar energy absorbed by the concrete and the brick, and the tile roofs, etc. And that absorbed sunlight then re-radiates in the mid-infrared, and what we call heat radiation. And so that adds to the temperature of the environment in those cities. So that is another variation which we're familiar with, in addition to this overall warming by added greenhouse gases. Okay, so, but there's even more. In addition to the urban heat island effect, we also generate and consume a lot of energy using various technologies. And that can worsen the warming, especially on a regional scale. This is called anthropogenic waste heat, and just about every industrial process that uses combustion adds to this. Okay, so I'm going to get into this a little bit more deeply, and we'll begin with the first premise that the observed rise in average global atmospheric temperature is about 0.6 degrees Celsius over the past 50 years, from 1950 to 2000. That is a real observed rise. And that premise number two, humans contribute waste heat to the atmosphere through their industrialized activities. And you can actually look it up, and you find that the power, P, the power produced by humanity, is around 15 trillion watts. The W means watts right here. And that's what we dish out in terms of generating energy and consuming energy. And most of that energy ends up back out. It gets re-radiated into our environment. And the basic thermodynamics, the principles, can be modeled and understood by high school and undergraduate students as well. So that's premise number three. And so I'm going to show a few equations now which will quantify this sort of warming, this direct warming by our industrial ways. Okay, so we begin with the Earth science in terms of trying to figure out what's being warmed, and we start with the atmosphere. The Earth's atmosphere, get a barometer, and you can find out that it has a pressure of around 100,000 newtons per meter squared. That's newtons of force per meters squared of area, and that's your pressure. So we also know how big the Earth is. It's about 6,378 kilometers in radius. And so using that, we can figure out the actual weight of the Earth's atmosphere. You just basically take the pressure, which is a force per unit area, multiply by the area of the Earth, the surface area of Earth. And so that's the pressure times the formula for area of a sphere, 4 pi r squared, and you end up getting a whole bunch of newtons of force. That's the weight in the international system, System International units, okay? You can now take that weight and find out what the mass is. So the weight, the force, weight is a force, that's equal to the mass times the acceleration of gravity. You've perhaps heard of Newton's F equals ma. Well, this is the same thing. The weight, F, is equal to mass times a particular acceleration, the acceleration of gravity on Earth. And so you can solve for the mass of the atmosphere, and that's the weight, F sub g, divided by the acceleration of gravity, which we know by dropping balls. You can figure out how fast a ball drops. And you end up getting a whole bunch of kilograms of mass, okay? And that mass is a lot, but compared to the Earth's solid mass, if you took a ratio and the percentage of that, mass of the atmosphere and divided by the mass of the Earth, you'd find out that it's barely 10,000th% of the Earth, of the total Earth. So our atmosphere is just a bit of a scrim around the Earth, and that's one reason why it's so easily warmed. It's not that substantial compared to the rest of the planet. Okay, so we now have the mass of the Earth's atmosphere, and we want to know how much energy would be required to change the temperature of that atmosphere by the amount that we see, the temperature change of 0.6 degrees over the past 50 years. And so this is basic thermodynamic theory taught in high school. The heat, that's the energy, the heat energy is equal to the mass of the atmosphere times the heat capacity. That's basically the amount of energy needed to raise a kilogram of the atmosphere 1 degree Celsius, okay? And, but we're gonna have it go over 0.6 degrees Celsius, and we're gonna use the heat capacity of the atmosphere, which is known. And you end up getting a whole lot of joules of energy, heat energy, 10 to the 21 joules of heat energy. So that's total amount of energy. Power is the rate of producing that energy. And so that you take that amount of energy, you divide by time, that will give you the power requirements for this temperature gain to have occurred over the past 50 years. So you take that energy, divide by 50 years in the right units of seconds, and you end up getting around 2 trillion watts, okay? That's what would be necessary to power the atmosphere so that it warms by 0.6 degrees in the last 50 years. You can compare that power estimate with the amount of power that we are dishing out in terms of our energy generation, and that's 15 trillion watts. And so you find out that the power necessary to raise the Earth's atmosphere's temperature by 0.6 degrees is only 0.13 of the power that humans are providing. Another way of saying that is that, let me get this, about 13% of the human power production as waste heat would fully explain the atmospheric warming. So, gosh, maybe this is the cause of the atmospheric warming and not the greenhouse gases. Well, wait a second. We neglected that other things are warming. Other things are warming, not just the atmosphere. There's the oceans, the land masses, and the ice caps. They're all taking their turn absorbing some of this energy, this excess energy, all right? And they will be rising in temperature accordingly. And so I actually had my Rockport High School AP Physics students work on this to estimate the power requirements to warm the oceans and land masses by similar amounts of temperature gain. So they had to research the depths of the ocean and land to which external warming would extend, because this is all beginning in the atmosphere, and then the atmosphere warms the oceans, the land, and the ice caps. And so they had to figure out, well, how much ocean, how deep do you go, how much land, how deep do you go, et cetera. And so there were also lots of uncertainties having to do with the measured changes in temperature of the ocean and the land and the ice caps compared to the atmosphere, and the heat capacities of the land, et cetera. And so, but they went through it, and beginning with the ocean, you can see with this plot that the temperature of the ocean drops with depth. It goes down with depth, up down to about 200 meters, and then it doesn't drop as much. The temperature does not drop as much. You know, it dropped more than 10 degrees Celsius in the first 200 meters, and in the second 1,000 meters, it only dropped by about 5 degrees. And so one would say here that most of the ocean that is being warmed has a depth of around 200 meters. And that in that way, you could determine the mass of ocean that is actually being warmed. AP Physics students, they found different thermal mixing thresholds at depths of 50 and 90 meters. And also, different sources said that the temperature increases in the ocean, they differed from 0.1 degrees to 0.7 degrees over the past century. And so there are some uncertainties with these figures. But no matter what those uncertainties are, the estimation details, it's clear that the ocean's heat budget rules. And you can see that by making a calculation for the mass of the ocean, the heat capacity of ocean, and the change in temperature. And I end up getting around 4.4 times 10 to the 22 joules, and the corresponding power output or received by the ocean is 2.7 times 10 to the 13 watts. So that's 10 times greater than what was calculated in the atmosphere, and 2 times greater than what we humans produce in terms of both the heat energy and the power. NOAA, which is, I would say, a more authoritative source, they end up getting even more energy in the ocean, about 10 to the 23 joules, and 6 times 10 to the 13 watts. So that's 60 trillion watts. And that would be about 4 times greater than what we humans are producing in terms of energy and average power. So now you can see that the oceans, in order to heat up just the oceans alone, this waste heat is not enough. So it is that greenhouse gas warming, which really is the winner. And just to show you how big sink of thermal energy the oceans are, you have this plot here, which shows the amount of energy, thermal energy in the ocean. And I don't quite get the minus, but as a function of time. And you can see a gradual rise, a gradual but significant rise in the heat content of the ocean. And then you can do the same thing for the land masses. The sun beats down on the land and it causes changes in temperature down to 1 meter on a daily basis, and down to 9 to 12 meters on an annual variation. You know, the difference between winter and summer can be felt down to that much distance, that much depth. Again, there's uncertainties having to do with the heat capacity, you know, how much energy is required to change the temperature of rock, 1 degree Celsius versus sand versus gravel versus permafrost, etc. There are uncertainties there. But I ended up getting estimates which are very similar to that in the atmosphere, that the heat required to warm up the land masses, the exposed land masses, are around 10 to the 21 joules, and the power is around 10 to the 12 watts, down to 10 meter depths. Okay, so reiterating the ocean rules in terms of having the greatest heat content, thermal energy stored. The land and the atmosphere and the ice caps only get you up to about 10 times 10 to the 21 joules. The ocean is more like 230 times 10 to the 21 joules. The ocean just has so much more heat inside of it stored, and that's the heating since 1960. Okay, that's what's been added, and the direct heating due to our waste heat is around 10% of that. This would be around 20 or so, 20 times 10 to the 21 joules. That's what we humans could have produced through direct heating. So although this waste heat is not the major contributor to the overall heating, especially of the oceans, it can be significant. And it can be significant on a regional scale, especially if you fold in the heat islands. And so here is a map. This is a model based on our energy generation and consumption. And it's regional, and you can see that there's only a few areas in the megapolis on the East Coast here, and then a little bit in Japan, And then in Europe, that's where the heating exceeds that produced by the greenhouse gases. That's supposedly at around 2.5 watts per meter squared, 2.5 watts of power per meter square of area. And so already we have regions where the heating, due to this waste heat effect or the heat island, or added to that, is exceeding the average warming due to the greenhouse gas emissions. And in a extrapolation and a forecast, you can see that the entire northeast seaboard and the east coast of China and much more of Europe will exceed the greenhouse gas warming. And so this is something to think about, something to worry about. Someday it may dominate the global climate. But right now there is a significant regional effect, according to these models. So I have to go back to 1971. It's now 2020. So we're talking about close to 50 years ago. John Holdren, who was former director of the White House Office of Science and Technology Policy back in the Obama administration, he wrote back in 1971, and I quote, that global thermal pollution is hardly our most immediate environmental threat. It could prove to be the most inexorable, however, if we are fortunate enough to evade all the rest. So I would have to say that John Holdren was very prescient in that statement. So that's what's happening on Earth. We do have this added effect. In addition to the greenhouse gas warming, there's the direct warming by our power generation. So what can be done about it? Well, first you need to phase out electrical power generation via these hot running methods. So those would include burning fuels or splitting atoms to make steam that then turns a turbine. So any coal-fired plant or oil-fired plant or natural gas-fired plant or nuclear power plant would be regarded as a hot running energy power generation technique. We want to phase those out and replace with the cool running power generators, which are based on the energy of motion, primarily hydro, wind, wave, and tide-driven generators. In addition, solar power is neither hot nor cool running. They do get warm, those solar panels, so they do absorb some solar energy and we radiate it into the environment, kind of like an urban heat island effect. But it's these ones which are making steam to drive generators, which are the major problem. And so here we have a typical power plant. This is the smokestack you can see, and this is a thermal infrared image with the exhaust gases glowing brightly. And then they also have, I guess, cooling ponds here and there. This is a typical power plant. I think this is probably a coal-fired plant. And replace those with these wind generators, which is local to us here in Gloucester. And that would be preferable in terms of this particular problem, the problem of waste heat pollution, thermal pollution. All right. Also at the receiving end, you can hold on to your heat rather than just giving it away. You can go from a poorly insulated building here, which is radiating the heat that is being generated through probably the combustion of fuels or any number of ways, to this building, which is better insulated and it's not giving up its heat. So the heat is being used where it should be used, and rather than polluting the environment. That's called energy conservation. And finally, you can work on stabilizing the human population. And this is a map of population density in the world. And you can see that there are favored places, but we know that the population is continuing to rise in a way that's unsustainable in the long term. And there's projections that if the fertility rate remains constant, we will have, here's 2020, you're going to have a population that goes past 20 billion people. Right now, it's at around 7 billion people. All right. And if you can, there's different scenarios, but if we can get a handle on our population increase, then maybe this medium trajectory would be what may happen. And the reason why population is important is because our fuel use trends with the population, or it has been for a long time. And so as the population goes, so too does our energy generation and fuel use go accordingly. So those are kind of hard truths having to do with this problem. So in the meantime, what's next in thermal energy research? This is a bird's eye view of a power plant. I think this is the smokestack, I'm not really sure. And it is eliminating its waste heat. Most of the energy that it generates ends up being in the form of waste heat. Around 70% ends up just going to warm the environment. In this case, it's warming the surrounding ocean. And so this sort of ground truthing using thermal infrared imagers, there's a call for it. You know, where are we polluting the environment in terms of our waste heat? That would be something worth doing, is to get a better handle on our sources of thermal pollution. All right. Other things you can do is to participate in organizations such as the Climate CoLab, I think, or CoLab. It's an organization out of the MIT Center for Collective Intelligence, and you can get involved. They have contests whereby you can submit your project, which will do something helpful in these regards. And one of my favorite projects that won a prize is the city of Calgary in Alberta, Canada. And they have a program in that city whereby citizens are encouraged, actively encouraged, to improve their waste heat score. First, every residence gets a picture of its rooftop, which shows where the energy is leaking out. You can imagine in Calgary it gets pretty cold, and so one of the problems is the energy leaking out on a cold day. And so you can see where the problem is, and then they give you a score as to how much waste heat you're producing and how it compares with that of your neighbors. I like that. And then they provide you with solutions to save money and to reduce your waste heat and corresponding greenhouse gas emissions. And so it's a whole put together, which I think is rather impressive. Okay. Finally, I would be remiss to note that this waste heat that our civilization is producing could be a clarion call of other civilizations on other planets. And so perhaps we could use this waste heat signal as a way of inferring the presence of techno-powered alien civilizations. Is this possible? Well, people, not including me, I'm just beginning to learn about this. People have been looking into this, and they already have put together this thing called a Kardashev scale, which considers which type of civilization you're dealing with. The type 1 civilization harnesses all the resources of the planet. Okay, so that would include the sunlight reaching the planet, but all the other energy sources available to it. Okay, and according to the scale metric, Earth rates around 0.7 on the Kardashev scale. Type 2 civilizations would harness the sun's energy entirely. It would the civilizations would exist in a shell, spherical shell, around the star, and that would be known as a Dyson sphere, named after the physicist who thought of this first. And that would, by harnessing that amount of power, you're dealing with, a lot of power, 10 to the 26 watts coming from the sun, for example. And then they even extrapolate to a type 3 civilization, which somehow manages to harness the energy from an entire galaxy. Okay, so people are taking this sort of idea seriously, this idea that you can look for planets which are, or planetary systems which are especially hot in the mid-infrared. And so there's projects that are going for this, glimpsing heat from alien technologies, the GEHAT project. And then there's the Colossus Telescope project, which I don't know what its status is. It looks, I had some dead links looking into this, but it was funded rather nicely for a while. And the idea is to better characterize exoplanets, including whatever waste heat that might be emitted by these planets. So that's all I have to say about waste heat and changing climates. And I'll get back to stop sharing my screen, and wish you all the best. I'll get back to you next month for another episode of Doc Waller's Earth and Space Report. Thank you. Bye-bye.